Is shielding really necessary for your CNC electronics? Of course it's necessary, but I'm going to show you exactly what's going on in those wires. I'm going to show the electronics without any shielding. I'm going to show wire placement, cable placement, and show you what it actually is doing on the wires itself. And I'll go into a little bit of theory, but for a lot of you, this video may be a little bit too pedestrian. If you want to see my techniques and also if I'm doing something wrong, give me some guidance. So let's get started. For these tests, we're going to need to start with the components of a CNC machine. And that's going to be a CNC controller, a stepper motor driver, a stepper motor, a power supply that's going to power the CNC controller. But we'll do the tests with and without the power supply for the controller, because the controller only needs the USB power to power the signals that connect to the driver. A lot of the features of the CNC controller use a power supply, like the inputs and outputs. And finally, we need a power supply that will power the stepper motor driver, which ultimately powers the stepper motor. I want to do these tests where I'm just testing bare wire with no shielding whatsoever between the CNC controller and the stepper motor driver. I want to use relatively long wire because in a lot of circumstances, that's what will happen in the real world. So I'll take quite a good length, maybe a few feet of signal wire to give us the worst case scenario. And then I'll also test a shorter distance of a wire to give us a best case scenario. I'm going to be doing the same thing with wiring the stepper motor wires to the driver. I'm just going to start with the wires that you see here, but then I'll increase the length of these wires to show both conditions. Specifically, the inputs of this controller are especially delicate and generally run within a cable carrier that will carry the stepper motor wires or cable. And when stepper motor wires are very close to the input wires, like for a limit switch or something, the limit switch can trip unexpectedly. To be able to see what's going on between connections or what's going on inside of a wire, you can use a multimeter. But the problem with multimeters is it's going to be too slow to really see what's going on inside of the wire. Instead, you need to use an oscilloscope. Oscilloscopes come in a very wide range of prices. If you're going to be using a CNC machine and working with control electronics a lot, then it's probably good to get one of these. I'll have a link in description. This is a very, very inexpensive oscilloscope. You can also get oscilloscopes that connect to the computer, which just like this one has 3 channels, this one also has 3 channels. But this one also has the ability to connect to logic signals. And in this particular one, you can connect to 16 logic signals. Logic signals are way outside the scope of this particular video, but essentially you can decipher communication protocols. And if you want to know more about that, you can check out my microcontroller videos. For the signal wires, I'm going to be using 24 or 22 gauge wire. And all of the wire that I use is stranded. What I won't be using in this video are wire ferrules. You'll see in my other videos where I'm putting together CNC electronics, I do use these. And if you're curious, I do have a link in the description for these as well. I don't want to get too deep into the connections and how I connect and whatever, because I have a bunch of videos that show that. This is the ground, the X pulse, and the X direction. I'm screwing them in and making sure that I tug on them so I know that they're securely fastened. Okay, I have the minimum number of components wired up, and this looks like a complete mess. It's a rat's nest. And more often than not, in my 16 years of doing this, this is how I see a lot of CNC routers. It's just, the wires are just going everywhere. And this is not even using the power for the CNC controller, and no outputs or inputs being used. To briefly go over the connections, the power supply has power from the AC, and it's not plugged in right now, so even if I did touch it, it wouldn't do anything. It's always good practice to close this, no matter what. I have the power wires going to the driver to power the driver. I have the stepper motor connected to the driver in a bipolar parallel configuration, and that just means that I can get away with using less voltage. And I have the step, direction, and the ground connected to the stepper motor driver. Okay, so according to the general theory out there, this may actually work fine. And the reason why is because a lot of these wires are not running parallel. And from what I've learned is if wires are running in parallel with each other, like next to each other, for instance, going through a cable carrier, then the problem may occur. But if the wires are crossing each other, the problem may not happen. So I don't actually know if this is true or not. This is just information that I've learned from the internet. And I generally just separate the wires completely. So I don't come across that issue, but I did come across this issue when I was first starting out. And thank God I found it out at that time, because I've been able to receive this really hard learning experience in the beginning and never have to worry about it again. So this is one of the reasons why I'm actually making this video. Okay, so let's see if the theory holds true that even though they're kind of jumbled up and they're crossing and stuff like that, but they're not in parallel. Essentially, for the most part, they're not in parallel, except for, I guess, this portion right here and this portion right here. But they're a distance away from each other. So let's see if the stepper motor will turn smoothly. Yep, it's turning normally. It rumbles in the beginning because I have it at a very low steps per revolution, but that's normal. I should actually put something on here so you can see the spinning. Okay, let's do this again so I don't hit any wires. Looks like it's working fine. Let's make it go a little bit slower. Yeah, it looks fine. I have the probe for the oscilloscope connected to a wire sticking out of the step, which is the pulse plus. And I have the ground of the probe connected to the signal ground, which is the same as this wire here, the red wire going in. So let's take a look at the signal. I have the trigger about right here. 5 volts is around this location, and this is 0 volts here. So you can see that there is a square wave. So you can see that it's a pretty clean signal. There's no variations of signal in this range here. If it started coming close to the middle range, that's considered a no man's land, where the controller or the driver wouldn't know what to do with that signal. But it looks very, very clean, even though we're not using any shielding whatsoever. Now in this test, I have some of the signal wire in parallel with the stepper motor wires. And this is going to simulate a scenario where maybe you have the signal wires a little bit too close to the motor wires and they're in parallel. For some reason, maybe you needed to do that. I don't know why. I don't know of any scenario that would be, but potentially if a new person doing CNC electronics doesn't understand the signal interference that could be caused by higher power motor wires, maybe that could happen. But let's see if anything really does happen. Maybe nothing happens. Maybe it works perfectly fine. Let's see. And look at that. It works perfectly fine, even though these wires are in parallel. So let's take a look at what the signal looks like. And the signal looks identical. There is no difference between whether it was in parallel or not. And there's absolutely no shielding going on. So what's going on? Why isn't it failing? And I suspect it's because of what's going on this controller. This controller has a lot of protections here. You have the 5 volts coming in and also the data. This 5 volts, this is the only 5 volts that's powering the signals. You have the signals deriving from this microcontroller, and then you have those signals coming out of the microcontroller going to this chip here. And this chip here has 5 volts pumping into it, and it's able to maintain a very good signal, a strengthened signal out to these terminals. This chip right here is really serving as a bunch of transistors that have their own power and making sure that the signals have a very strong output from this chip. So at this point, it looks like we don't even need to have shielding. So let's take this example, and I'm going to lengthen some of the wires so I have a lot more wire going to a longer set of signal wires. So all of this signal wire, or maybe even a longer set, can be in parallel all the way along. And let's see what happens. I also want to show what's going on one of the ends of the coils for the motor. Because I have this set at full current, this motor is probably hot. Yeah, it's pretty hot. It's set at full current in idle. That's switch number 4. And I'm probing the B minus, and the ground is on the ground for the higher voltage. So I've set the probe to 10x, so because I don't want to show a 1-to-1 voltage on a 48 volt power supply. And I also set the oscilloscope to 10x for the probe. And you can see it's a pretty clean signal. It's not doing really anything special. It's just a square wave. And that is only for the purposes of holding the position of the stepper motor. By the way, as an aside, if you don't want your motor to run hot while it's on idle, just set the switch number 4 to half current, which is over here somewhere. Now I would like to see what happens to just a bare wire going through this conduit. So what I did is I took off the direction signal from the controller, which is already going through this conduit. And I want to see what that wire looks like on the oscilloscope with the system turned off and with the system turned on. So you can see something happening on that wire, but you'll also notice that this channel 1 is at 110 millivolts. So it's very, very faint. If I took that and brought it back to a level that you'd see it's sort of a 5-volt jump, this is 1 volt per grid line here. You can see it's barely even visible. So it doesn't even look like it would go into a no man's land scenario. So it looks like it generally would never jump up. Okay, I'm back to probing the pulse, just the pulse from the controller and the ground connected to the ground for the probe. And I'm going to crank up the oscilloscope so you can see what's going on this wire, even though it has a circuit to the driver and then completing the circuit with ground. So the circuit has a return. You can definitely see something going on here, but I have the channel sort of amplified 200 millivolts. So each one of these lines is 200 millivolts. If I went back to 1 volt, you can see you can barely see it, but you can definitely see it if I crank it up. So this is the interference coming from the motor wire. So this is 1 volt, which is the signal from the pulse from the CNC controller. The interference is really insignificant. You can't see anything unless I really crank it up. And it's never gonna get to the point where it's gonna cause a fault. Okay, now let's take a look at a scenario that's more extreme. I have the motor wires throughout this entire length and it ends up back at the driver. So the motor is connected to the driver, but it has to go through all of this wire, which has more resistance and has more length to create interference on the signal wires. So the signal wires also, starting here or at the controller, it's going all the way through this length of wire and coming back to the controller. So let's take a look at the signal of the pulse while this is connected. This is in idle state, so it is providing a pulse to maintain its position. So on the oscilloscope, this is the signal line for the pulse. So I moved this a little bit down so you can see the actual pulse going all the way up to 5 volts. Each one of these marks is a 1 volt level. So there would be a top of the square wave would be around here. You can already see that there is a interference just because the motor is trying to keep it idle at its idle torque. And I have the trigger at 1 volt. Actually, it's a little bit below 1 volt. So that is actually significant. And this is, I would say this is about 10 feet of wire. Now, the more interesting thing is if you move the motor, you'll see that the trigger triggers the signal, but it doesn't trigger the interference anymore because the interference is actually at a different frequency because the motor, this is only one of the pairs of coils. So the frequency of the pulse is not going to be the same as the frequency of the power going to the motor. It's going to be different. If I go down with the trigger level, let's see, we start to lose the pulse from the signal, and now we're getting more of the motor wire power interference. All right, in this next test, I want to see what the interference on one of the lines, which is the pulse line, as I remove it from being parallel, one section of this at a time, to see if the interference goes down. I'm going to move it down just a little bit more. I'm going to increase it so we can see exactly where the interference stops. Okay, so this is exactly where it's happening. So each grid line is at 200 millivolts. I want to take all of these away. All right, I just want to take this away here. So it looks like it did reduce. So I'm going to bring the trigger down and see where it lands. Okay, right there. So it went down considerably. So that's almost, let's say 100 and maybe 190 millivolts. Let's take another one off. So I would say that's about maybe 1.5 feet. Oh, I got to take this one off too. Let's go down. So that's almost a full from where it started, 220, maybe 230 millivolts. All right, let's take off another one. So it is definitely decreasing. So let's go ahead and see where this lands. Not too much actually, but it wasn't that much of a length that I took off. Having a, let's see, let's take this over here. Keep going down. Wow, this is a lot. That one went down quite a bit because I think maybe because I moved these farther away, but not sure. But it's definitely making a difference. Okay, now we only have maybe about 4 inches left over. All right, let's see where this lands. Okay, so the signal interference is actually really, really low. This is about 220 and then another maybe 170. So 390 thereabouts millivolts from here to here. Now let's completely separate the signal wire from the motor wire. I know I'm creating some inductance in this wire. Some of you may have already noticed that because the wire is being looped. All right, you can see that it needs to lower again. All right, so let's go up a little bit. So that's around maybe 250 thereabouts, 260. All right, I'm just gonna now just let this lay over the table. I'll also take the motor away. Now it is completely away from the motor cables. So now the motor cables are just going around the table like this, not touching anything. In fact, I'm just gonna go ahead and let it completely get out of the way of the signal wires. And over here, it's just laying off the table. So they're completely separated. And it looks like it lost the signal again, so I can go even farther down. Okay, so it does still receive the interference from the motor, but it's really insignificant. It's like maybe 170, 160 millivolts. And this will very unlikely get into the 2 to 3 volt range where it's going to mess things up. All right, so far we've learned that it does make a difference when you have motor wire and signal wire in parallel. I'd like to do another experiment while I have this set up where the signal wire is intersecting at various points. That looks pretty perpendicular or intersecting to me. All right, let's see, where does this, all right, so it's pretty high actually. So it's right about just above 220, maybe 240 millivolts. Let's add another intersection. That looks okay, I guess. Let's see how high we go. It's going up. All right, so that's about, it's not that much higher, but it's, let's say maybe 100 millivolts more than 220, so that's 320 millivolts. I want to get this one a little bit better seated here. All right, now I'm going to take another route. Okay, another intersection. It is rising. Okay, so that's about at the 440 mark, 220 plus 220. All right, so let's add one more. This is a little bit less of a loop. All right, so that's the last loop I can do. Still, it's around 440. Didn't really change that much. I have a number of intersections, 1, 2, 3, 4. Get the worst case scenario out of this particular scenario here. So I'm gonna do 2 more. It would be kind of hard to do just 1 more out of this. So we'll count this as 2. I got 1 more here. So now we have a total of 6 intersections, which is actually 12 intersections for each signal wire. So this would be the worst case scenario for this instance. All right, so it didn't really go that much higher. So in parallel, we were way up here, but in a scenario where we're just intersecting, it's about half as much. So intersecting does make a difference, but it's not as drastic. All right, so while I have everything non-shielded, I'm going to add 1 limit switch wire. To test the signal wires of an input that is connected to a limit switch, I added a 24 volt power supply connected to the 24 volt and DCM terminals of the controller. The probe is on the DCM of this particular circuit. The limit switch is connected to N1 and DCM. It's connected as a normally closed state. The ground for the probe is connected to DCM, which is also where the return of the circuit for the limit switch is connected. The entire wire of the input is in parallel with the motor wire. So let's take a look at the circuit with everything plugged in. This is with the same settings that I had when measuring the step signal wire. Each grid line measures 220 millivolts. So let me reduce that. This is every 2 volts. Let's go up. Okay, now it's gone. So there is almost 4 volts at the peak. I'm going to engage the limit switch to see what happens. It looks like the limit switch, because it's 24 volts, is way off the scale. So let me change the scale of the oscilloscope. I'm also going to increase the trigger so it triggers only that signal. It looks really, really noisy. This video is sponsored by me and my website, BuildYourCNC.com. If you need anything with regard to CNC, laser machines, 3D printing, check out my website. I'm kind of reinventing the website because competition has grabbed hold. I've been in the business for 16, 17 years, since about 2007. I want to provide a resource that will allow users of the website to find things that they are really able to find like on Amazon.com or from other resources. Although most of the products on the website will be curated, and they will have links to Amazon.com as affiliate links. That's really just a way to pay for the efforts that I put into it, and to allow me to survive and my family to survive. So it will help out a lot. I hope you go over there, check it out, and if you need something specific that you can't find on it, go ahead and give me a text. I have my phone number on the top left-hand side of the website, and you can text to that number, and feel free to let me know what you'd like to see on the website. I want to cater this website to you, but also informational resources. I've recently put together a list of 3D resins. It's a very comprehensive list. It has the water-based, medical grade, or structural type resins. They have a lot of information on each resin, like all the mechanical properties. And also, you can find the settings for certain printers in some of the resins. I haven't completed all of that. It takes a lot of time to put that kind of list together. So check out the website. I want to hear from you and get some information on what you want to see in that website. So you keep going back to that website and see it as a resource. Please give it a try and let me know what you think. So each one of these is 5 volts. There was a line here. I'm going to bring this up just a little bit more and engage. Okay, bring it down just a little bit more. All right, you can see that it is trying to trigger that. Okay, that's triggered. All right, it actually goes way above the 24 volts, and that's from the interference. It seems to be happening at the same frequency levels. So let's see if that's true. Yeah, so it happened about right here. There's the penultimate grid line or grid area here. Let's go back up. So it's actually the same location. So you can see that the interference is quite significant, but it doesn't seem to go into that no man's land of where it's going to trip. I want to change the position so we can see the whole thing. So what I want to do is I want to keep it like this, engaged, and I'm going to move it off of the parallel one section at a time like I did with the other signal. So I'll just keep it engaged with a simple binder clip. Let's see where I should put this. The 0 volt is around here, so I'm going to put that at the very, very bottom. Okay, so now the 0 volt is actually at the very bottom, so when I engage, okay, so now we can really see the number of volts. So right now we're at 35 volts right here. Let's take off one section, and it reduced about maybe 2 volts. I'll remove another section. So that's about 2 feet. So now we're at about 29 volts, 28 volts. Now we're at about maybe 2.5, close to 3 feet. I'm gonna put this on the ground here. All right. Okay, so it looks like we're at the about 28 volt, about 27 volts. We're getting very close to the 24 volts, which is good. All right, there's only very little remaining here. So we're just about at the 26 volt level here. You can see that that's around 23 volts, which is, close enough to 24 volts. And now I'll completely remove it from the area. Now the signal isn't anywhere near the motor power wires. It has about maybe 3/4 of a foot distance. And it looks like we have a pretty clean signal here. Let's see if we can find any trace of that motor. I don't see anything. There is no evidence of any interference on the signal now. I want to put it back in parallel because I want to see when it's not engaged, because that's generally when it's going to be more critical. All right, make sure everything is close. So where is the voltage here? It doesn't seem to be that much when it's not engaged. Let's go, okay, so right there. I'm going to bring this up just so we can see the signal a little bit. All right, so we're about 4 volts. Yeah, it's the same as we measured last time. It seemed to make a bigger difference when the limit switch was engaged. So let's think about this, because it doesn't really make intuitive sense why there would be more of a difference in the interference when it is engaged. But when it's engaged, only one of these wires is actually making the circuit, so it doesn't actually get back to ground. So remember in the other scenario, we were measuring the pulse and the interference on the pulse. It actually had a path back to ground. And when we're engaging this, it doesn't have that path. So it's essentially like an antenna. Okay, so now let's change the setup. I'm not going to repeat the signal wires that connect the controller to the driver because those are generally going to be short. They're going to be in the same box together. So, and we've already tested a very short parallel scenario, and it didn't really make that much of a difference. So I'm going to leave that test out, but I would like to see a test with just with a shielded wire for the input and no shielding for the motor. And then we can look at shielding the motor and non-shielding the input. And then we'll do both of them. We'll shield the input and shield the motor and see what those differences are. All right, in this scenario, I have a shielded cable with two conductors. One goes to the input and one goes to the ground. And the shield conductor, the little shiny conductor here, is also going to the ground, so all interference goes straight to ground. In this context, the ground is the DC common, which is DC ground, DC V negative, as it's shown on the power supply. The cable is parallel to the motor wires throughout the length of the motor wires here, finally ending up here. So looking at the oscilloscope, this is the 0 volt line because the limit switch isn't engaged. If the limit switch is engaged, you'll see that it will pop up to the top. And that will be the 24 volt or 23 volt line. And we can see that there is literally no interference at all on this line. One thing to note is in the cable, the shield is not connected to the ground or on this side of the circuit like it is here. According to what I've learned, or the literature that's out there, is that you only need one side of the shielding connecting to ground. In high frequency applications, you have to connect it to both ends, but this is a very low frequency. It's only going to be on or off. Now let's take a look at a situation where the motor cable is shielded, but the signal cable is not shielded. All right, in this scenario, we have the limit switch signal wires in parallel with the shielded motor cable. There is a little bit of exposed non-shielded motor cable here. Actually, I think I may want to add just a little bit more just to give it a worst case scenario. Although this probably won't ever happen because the motor is most likely going to be mounted farther away from the limit switch. But if you do have a scenario where there is exposed motor cable, non-shielded, in parallel with a more delicate signal cable, you can easily shorten this length of wire here and make sure that there's more shielded cable closer to the motor. All right, there does seem to be some interference, it looks like. Let's go down and see if it matches the motor interference. Yeah. It's sporadic, but it's there. Let's see if when I engage the switch, it shows something. And I don't see anything there. No, the trigger can't pick up anything. So it still looks like a pretty clean signal, even though a little bit of the wire is exposed. So like from here to here, there's really only maybe 8 inches, 9 inches of exposure to this non-shielded portion of the motor cable. So it looks like this is also a good alternative. In this final scenario, the motor wires are completely shielded. The input wire is completely shielded. So you have the best case scenario for the success of the cabling. It's almost a useless scenario to demonstrate, but it wouldn't be a complete demonstration overall unless I included this. The driver is on and the motor is holding. Yep, and it's getting hot. And this is at 5 volts per division. And it looks completely clean. No problems on the wire. If I enable, you can see that it goes into a high state. When I release, it goes to a low state. And this is also with some of the wire exposed without being shielded. In a typical CNC scenario, this would most likely be closer to the motor, or this wire would never even come close to this part of the motor. Even if the limit switch is really close to these wires, there's still no interference on that line, you can see. Okay, so we can see that with or without shielding, it does make a difference, but it doesn't make so much of a difference that the interference is causing a problem with the signal. It does show up in the signal, but it doesn't seem to be affecting it to an extent where it goes into a level where the controller may not understand the signal. The fact that you can see the EMI in the signal cable means that you should probably still shield either one of them or both. If you're looking for a pristine signal, I would go ahead and shield both of them. It's not really going to hurt anything. But in my setup, I only provided a certain length of cable that is in parallel. And in this scenario, I only provided a certain length of cable or exposed wires. In a real world scenario, you'll probably see either less or more of that. So if you have a scenario where you have a larger machine and there's a lot more cable run through the cable carriers, you might want to shield both of the runs of cable or either one. It's really up to you. But you can see from the experiments that shielding only one of the cables does provide a very clean signal. I didn't really go into the idea or concept of using a shielded enclosure. So most of the enclosures out there are metal, and these enclosures provide a certain level of shielding from any outside interference. If you're inside of an industrial setting, you may want to opt for a metal shielded cabinet and then make sure that the shielding of all the cables and wires are connected to that metal cabinet. That metal cabinet will serve as the ground and the path for the interference to go. I think these set of experiments will provide a pretty good idea of what you'll expect in a CNC or a CNC environment. I didn't do any experiments with multiple motors or multiple signals, like if you have more than one limit switch. This is only a single one. It is kind of an experiment to understand less complexity, less variables, and you can understand where to go from there. Looking at taking away the delicate signal wire from the higher power motor wires in sections should give you a good idea of how interference happens and how you can maybe avoid interference altogether. I hope this video helps, and if you have any questions, please leave them in the comments. Please don't forget to subscribe if you haven't subscribed before, if you enjoy these videos, and press the like button to help my videos and help my channel out. This is a very niche channel, so I could take all the help I can get.